Give me a second. Yeah. So what we're planning now is so this is the so we just to emphasize, we intended this induction lecture to simply be up on the Nalanda website for posterity forever. So anybody who comes later can come and see, what this is, what this is about, what the basic concepts are, and go from there. So some of you found it too basic, and some of you maybe found it that we didn't spend enough time on certain concepts. So we're still learning how to do that, and we will get better. Now, what's happening next is that we are going to start a next module, which will be much more practical. So we're gonna, the theory part that we covered here. If any new theory we need, we will cover it as we go along. We're not focused on theory. We'll be very, very practical. And what we're doing in between, while we plan it, is we're going to have a little coding academy. So we're going to get people, some volunteers, and Ramiz and myself will also be a part of this, to go through basic Python and RStats coding. This is software called RStats that people use all the time in data science. And if you go on these websites that sort of lay out a career path for people who are interested in data science, these are the two main software packages. So this coding academy will be independent of the course, and we're going to open it up to anybody that just wants to learn it as well. And then once, I think this will take like 1 or 2 months, and then once we're done with this coding academy, we'll jump into the next module. And the next module will be very, very application heavy. And each application we're still deciding which ones to go through, but each application will cover. So so this one will really be like on Google Classrooms, and then there'll be a co-laboratory or something. So there'll be a lot of coding, and there'll be a lot more practical exercises dealing with real data sets, cleaning data. So it's really going to be hands-on. And then afterwards we'll have a hackathon, and that'll be the end of that'll be the culmination of that module. And then is a decision whether as to we go to more advanced, like really final, final boss level data science. A lot of the theory, a lot of the stuff that we're covering now. So at the end of this lecture, if I get to that, I should hurry up. I'm going to introduce you to some, very, very advanced concepts. You have been introduced to some very advanced concepts, but maybe just you haven't seen the details behind them. So there could be a more theory intensive final, third module, or we go straight into machine learning, which is fun. Actually, it's something that then you can, then go in, write your own codes and make your own neural network. Of course, you need access to good compute, at least a decent laptop to do it. But that's what we're planning. So this is the final induction lecture. But don't worry, we're continuing. We might just take like a pause of 1 or 2 weeks to assemble a team to do the coding academy, and then we'll take it from there. And of course, I would like you to share with me any feedback you have about how this went for you. So what I've noticed is that there's a fairly, a small group of people that are very dedicated and they come all the time. Yes?
Hello.
Yes. Please speak, yes. Mahesh, okay, I thought Mahesh had a question. So if you have any feedback, any comments about how it went, because Ramiz and I weren't sure whether we were either boring you, whether you already knew a lot of the stuff we were talking about, and it was too basic for you, or we went too fast on some things. So this is information that we could really use. But okay, let's begin with today's lecture, and just go back to having my camera pointed to my worksheet so I can do some equations if I need to. Here we go. Yep. Okay. Can you see my handwriting right now? Is this visible to you?
Yes, sir.
Oh, you can see. Okay, good. Okay, so let's now let me now begin with.
Sir, can you slide little bit your paper towards left? Then it will be a
Yeah, no, I'm actually going to give a lecture now first. I'm going to give a lecture first. So you will now first just see this. So can you see my screen? It should be slides now. Can you see the slides?
Yes, sir.
Okay,
Yeah.
good. Okay. So let's finish our brief but hopefully informative introduction to election polling. So last lecture, so it's been a while since our last lecture. I apologize. I've had a lot of changes in my schedule. Um, and we covered this concept of sampling error. And it may have seemed a bit mysterious because I just asserted some results that come from applying the central limit theorem to a normal distribution. So what we're going to do today is we're going to flesh out the details with discrete statistics and hopefully in a way that you should be able to reproduce for yourself. And through a very simple example, and we are actually going to do an election poll. We're going to actually theoretically we're going to do a thought experiment of what an election poll would look like. Okay, and so and
Sir,
we'll see the sample.
sir,
Yes.
sir, sir, excuse me. Sir, is this the, I mean, probability mass function is for discrete random variable and probability density function is for continuous random variable. Is this
Yeah.
the
That
right?
that 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 is that. Yes. That is one way of defining it, right? I mean, those are definitions, but yes, what you're saying is correct. Yeah.
Okay, I was confusing. Okay, sir, thank you.
Yeah, yes, yes, no problem. Yeah, yeah. So you have to be aware that sometimes different textbooks and different mathematicians and even different scientists have different definitions for the same concept. So whenever you see something like this, Modish, you have to not necessarily focus on the words, but focus on the equations that they're using to describe those words, and then make the connection yourself sometimes. Um, and this you will encounter a lot. But indeed, what you said is correct. So what we're going to do now is we're going to actually derive something very interesting, which is the size of the sample you need to arrive at a given accuracy of a given statistic, say, for example, the average of something, um, with some underlying probability distribution function. So in the previous lectures, we saw that if you took this example of flipping coins, 1,000 times and taking the average of those coin flips, and then repeating that experiment 10,000 times, that the net outcome is this sort of Gaussian shape, this normal distribution shape with a variance. And by the way, when we say 10,000, the number of trials here is 10,000. So we've done the average of 1,000 coin flips 10,000 times, and this width is given by this formula. So this is just thrown at you. Okay, so let's derive this now. Let's actually arrive at this where this comes from. And there is already something very interesting apparent in this, which is the width of this distribution didn't actually really care about the number of actual. You see, so I could have taken the average of not of 1,000 coin flips, but of 1,000,000 coin flips, right? And I would still get a width that is proportional to the number of times I repeated that experiment. In this case, it's 10,000. So let's first understand this a little bit better, and we will go through this in the problem set. I think Modish asked me a question about this, but so we will see this later. But if you happen to do the problem set, it's very straightforward to see that imagine you have some random event, and that random event comes from some underlying probability distribution function. And so every time you repeat the trial, or you repeat a draw of something, what if every time you do it, you're sampling from the same underlying random distribution. Okay, so in statistics, it's known as an identical independent draws of identically distributed random variables. And if the underlying variance is, let's say, something sigma squared, then the sample variance for a sample of size n is given by sigma squared divided by n. Okay, so that means that if you're trying to, let's say, construct, let's say the average of something, then the more times you sample the thing, the more you're going to get accurate to the actual value of the average. And so we will actually do this explicitly in a slide or two for an idealized version of an election pool. So the idea is so where does this square root, this p minus 1 over n comes from over here? It comes from the following fact, is that if the variance itself, if the sample variance goes like the variance for one event divided by n, And now consider the situation where we have a binary random variable. That means the outcome is either yes or no, 1 or 0, heads or tails. And if the probability of one of the outcomes, let's say the probability of obtaining a 1, probability of obtaining a heads, etc., is, say, p, then the probability of obtaining the opposite outcome or the other part of the binary, so in this case it's 0 or it could be tails, is 1 minus p. Then clearly the average is given by p times 1 times the probability of getting a 1 plus 0 times the probability of getting 0, which is just p. We do the same thing for the outcome squared. So now it's the probability of obtaining a 1 times 1 squared plus the probability of getting a 0 times 0 squared, but that's also just p. Okay, so if we construct what we mean by the variance, which is the average of the square minus the average squared, it's just p minus p squared. And so therefore, if we repeat this, so the variance, the sigma squared is just p times p minus 1, and then the sample variance, if we do this, repeat this experiment n times, by this result, which we will derive in a second in the problem set, or was trying to explain the problem set, is just p times p minus 1 divided by n. That's what we're seeing here. Okay. So, notice something peculiar, right? Is that this width actually doesn't seem to care about the number of trials we did, the number of coin flips we did in each trial. I could have done 1,000,000, I could have done 1,000, right? All it cares is that the number of times I repeated that one, if you like, trial. And a trial consists of the average over some number of coin flips. So that's already telling you, this is already giving a hint that the population size is not entering the sample variance. Okay. And this is something that we will see explicitly here. Okay, so the idea is, so this is the surprising fact about election polling. It's got to do with the central limit theorem. We're not going to prove the central limit theorem, but we will see it. At work here. Is we're going to do a thought experiment where as if we are conducting an election poll, and very quickly you will see that independent of the size of the population, what determines the size of the sample you need to get, so let's say you want to get a 1% accuracy of your estimate of who is going to win the election, the size of your sample needs to be no more than 10,000. And it doesn't matter if you're doing this experiment for, let's say, a district level election or election the size for a country of India. So the population does not enter. So if you really had a truly, truly random sample, then asking 10,000 people in India, well, let's say we had a presidential election, which we don't, right? But in the cartoon example of you just either vote for the president or the prime minister or not, and you don't vote for parliamentarians, that if even it's 1.3, 1.4 billion people voting, you will get to within 1% accuracy of the true result by only asking 10,000 people. And in fact, if the size of India wasn't 1.3 billion people, but it was also just 1.3 million people, right? It was 1,000 times less. You would still find that the sample size you need to get to 1% accuracy is 10,000. It doesn't change very much, if at all. In fact, it doesn't change at all in this simple example that I'm about to go through, and I will show this explicitly. So why? Okay, so let's do this. Let's do this thought experiment. So consider a population of m individuals. Okay, m is a big number, and k of whom intend to vote for candidate 1. So that means m minus k will vote for candidate 0. So the number, the proportion of people that will vote for candidate number 1 is k divided by m. M is the total population. If this number exceeds a half, then candidate 1 wins the election. Okay, so, but let's say we don't know whether this is a half. We just say that k over m is some fraction. It could be a half, it could be a third. If it's less than half, the candidate loses. If it's more than half, the candidate wins. What we're just trying to do is we're trying to estimate from asking some finite n number, n is much less than m, of people, of sample, of, if we ask a sample size of n, how likely will sample size of n, how accurate will it be to estimate this actual number that exists? So obviously, if you ask everybody, you would get the right answer. But you can't ask everybody. You're always asking a small number. So let's just think about this from first principles. So how do we do this? So imagine we just order the individuals in the population so that the first K, so we just give, we give them a number 1, 2, 3, 4. You're person 5, you're person 6, right? You just order everybody from 1 to n. And you just arrange the ordering such that all the individuals who will vote for the first for the candidate number 1 will appear in the first K, because we said that there's a total K of them. Okay, and then the numbers that go from K plus 1, K plus 2, K plus 3 all the way to n, those are the ones that will vote for candidate 0. So we're just taking the population and we're just ordering it in this way. Now the question is, here is m individuals. Okay, there's a lot of them, but now I'm just coming and I'm picking randomly 1, 2, 3, 4, 5, 6, up to n individuals randomly chosen from this set. N could be 4, n could be 10,000, right? We are asking the question, what would be the outcome of a random sample of n individuals? Okay, where n is less than n. So what that means is, I'm asking, what is the probability? So let's say I just picked n individuals at random from this population. What will be the outcome of that random sample? So let's say I picked, let's say n is 4, right? And so then I could pick all 4 from here, in which case, the probability is 1, right? That I've estimated the probability to be 1 rather than k over n. So I'm wrong, right? Or alternatively, if n is 4 and I pick them all from over here, I'll get 0, right? Because the average of 0 is 0, even though the actual average is k over n. So, but if I picked, let's say 2 from here and 2 from here, then I'm getting a half, but I don't know what k over n is, right? So this is really the game that we're playing. So it's a combinatorial problem. Okay, so these are some equations, and if you're familiar with combinatorics, fantastic. But even if you're not, I'm going to explain it in a second. And some students asked for a more detailed explanation about what these numbers mean and how do you arrive at them. So I found a very nice reference in this link. It does it very, very intuitively. You just have to imagine putting balls in different boxes to understand this equation. But the question we're asking, okay, so the probability that a given random of sample, so the fraction of individuals that you will find, that vote for, so we do a random sample. In our random sample, we have some number of individuals, I, who are drawn from this batch. And then the rest of the I, the n minus I, are drawn from this batch. Okay? And so the total number of ways in which we can choose n samples from m individuals is given by this quantity, m choose n. Okay, so this is saying that if we have 1,000,000 candidates and we sample it 100 individuals, then there's this number of ways in which you can distinctly pick 100 individuals from 1,000,000. And this is some very, very big number. Okay, this factorial notation means m times n minus 1 times n minus 2 times n minus 3. Okay, but if you understand this, great. If you don't, please suspend your disbelief and just read up on how we arrive at these numbers by following this reference.
Sir, can you send this link on, those classroom comment
Yeah, of course.
section?
Yes,
Because in slide we can't copy that.
Yeah, of course. Yes, I was planning.
Okay.
Yes, yeah. Okay, but you don't need to know the precise details of this. All you have to do is think about what. So pretend you don't know how to calculate these numbers. If you know how to calculate these numbers, here's the answer. But even if you don't, we're just engaging in elementary probabilistic thinking. Okay, the total number of ways in which you can sample n individuals from a population of n, m, is given by this number. And the number of ways in which you can sample n by having I samples drawn from here and n minus I drawn from here is given by the product of the two, right? So if I'm drawing, let's say 3 samples from here and n minus 3 samples from here, then I need to know the number of ways in which I can pull 3 samples out of k times the number of ways in which I can pull out n minus I samples from n minus k. And this is just telling you the number of ways in which you could have arrived at the number I divided by n. Okay, so if I is 0, what is the probability of estimating that nobody's going to vote for this candidate? Okay, that means all of your sample, all of your random, all of the individuals that come from your random sample must be here. That's the only way you can find that nobody votes for candidate 1. So the question is, how many ways in which you can pull out, and how many ways can you choose n candidates out of m minus k uh, uh, entries that are all 0, right? And choose none from here. Okay, so that's k, choose none, m minus k, choose n. And then we divide by the total number of ways in which you could have chosen n candidates in general, and that's this number. Okay, so what we've done is we've set up a Google Collaboratory where you can actually, so I will send a link to this as well. Okay, so what we can do is, so I'll send a link to this so you can play around with can, I guess you can still see my screen? Can you see my screen or no? I guess not.
Screen is visible, sir.
It is visible. Okay, I thought I lost you guys for a second. Okay, so good. So, oops. Yep. Okay, so the net outcome is just from this example. This is the distribution of estimates of the number of people that are going to vote for K. Let's say M is 1,000,000, right? And we're only drawing 100 samples. But let's say half of the population is going to vote for candidate K. So the election will be a draw. Okay, it's a fictional universe. Okay, so the true probability is a half, and we're doing 100. We're just pulling 100 random individuals from this sample M, and out of these 100 trials, these are how they are distributed. Okay, so the most popular, the most frequent outcome is half, right? Is 50 in this case, right? So but notice that there's a width, right? So sometimes you're going to be off. Sometimes you're going to be quite badly off. Sometimes you're going to think that the election is going to be a strong win for candidate 1. Sometimes you're going to think the election is going to be a strong loss, right? And so this is just from the exercise of counting the number of ways in which you could have pulled out, individuals and have arrived at, and you ask them what their choices are. You realize that that depending on how you do the sampling, you could either get that the probability is very, very different from the actual outcome. But if you just sample them all from here, or you just sample them all from here, but very likely you're not going to do that. That's a very unlikely event to happen, because it's very rare that you'll have all the samples coming from here. If you just pick them at truly random, then you're going to get some mixed up. And so it's a way to estimate, it's a way to calculate what those probabilities are. You have to figure out the number. If you're assuming that each random way to pull out the candidates is equally likely, it just corresponds to the number of ways in which you could have sampled the population N by picking some number from here and some number from here. And if you work that out, and so I will set up, I'll send you a link to the Jupyter notebook that actually does this. So look what happens. So this is for a sample size of 100. This is what happens when you take 1,000. Okay. So now the sample size is 1,000. Now what we're having is that many, many more. So you see, so out of the 100, and by the way, this number is basically 0. You can forget it, right? But out of the so out of all of the 100 different trials, these are the different results that people are getting. So imagine 100 different people did this sampling. But if we did this 1,000 times, notice that the peak is becoming more and more sharper. The width is becoming less and less. The sample variance is going down as I make n bigger and bigger. Okay, the sample variance decreases with n, as we found, and as n goes to infinity, we're just going to get a spike, right? Why? Because if n goes to m, rather, right, we're just going to get a spike. Why? Because if m goes to n, you've just done the election, and so you're only going to get one unique answer, right? Which is that it's a half. So the sample variance decreases with n. But what's more interesting is the following. You can't even see the difference here, right? But oops, what I've done is I've done the same exercise, right? Let's say, so this should always be a half. Sorry. What I've done is this should always be m divided by 2. But this is not 5,000. So whatever m is, this is a typo. I should fix it. Whatever m is, k is m divided by 2. And but what I'm saying is that my sample size is 1,000, and look at what I'm getting. If whether the population was 10,000, 100,000, or a million, you see, the width has not changed at all. Okay, this is saying that your sample variance did not care about the size of the population. So the error in an election poll is this width. Okay, is how big is your sample variance? Like, how sure am I that I've gotten the correct answer? And you see that for even a sample of 1,000, you've had basically, some percent error. I guess it's like 2 or 3% error, whether the population is 10,000, 100,000, or a million. And that's why election polling works, or it can work rather, is that in order to truly, and by the way, this would be true for understanding how what the population prevalence of COVID is in a population, right? Is you must if you truly sample randomly, then the size of the sample you need, even for a country of 1.4 billion people, if you want to be 1% accurate, is no more than 10,000. And it doesn't care about the size of the country. It could have been, it's the accuracy that determines the sample size. Okay, so you see, it's that if the bigger you make the sample size, the more and more the sample variance is going down, and that's the only thing that matters on the sample size, right? Is that the bigger and bigger I make the sample size, the more and more the sample variance goes down. But for a fixed sample size, you get the same variance no matter the size of the population, right? And this is really a consequence of the central limit theory, right? Is that once you get above a certain number, there's an exponential suppression of deviations from essentially just a purely random outcome. And so the sample variance is independent of the size of the population. And so what goes wrong in election polling typically is that your sample isn't random. You have, you're oversampling in one locality, or you're only looking at one section of population. You're using biased estimators. And so this is, so please, I think this is really something that if you just can follow through the homework problem, and you can follow through some basic combinatorics, you will arrive at a very intuitive and essentially absolutely correct interpretation of sample variance. Just imagine, do the experiment yourself, with rice grains at home or something, right? Just put out and color them like, some number, and then put a blindfold on and just imagine picking them out randomly. Let's say 10, 20, 30, or something like this. Of course, it'll take you a while to actually do the experiment in reality. But the idea is that you can calculate, if you just have a big sample, or it doesn't have to be that big, just some sample size, and you know that some fraction of them are going to go vote for one candidate and some other fraction is going to vote for another, and you just randomly pull out candidates, right? And then but you pull out only n of them, and then you keep randomly pulling out n. It's going to be very clear that the probability of obtaining a particular outcome from your finite sample size is going to be proportional to the number of ways in which you could have pulled out I candidates from here and n minus I candidates from here, divided by the total number of ways you can actually select, n total candidates from this m. It's just what this number constructs. The probability of obtaining I candidates from the probability of obtaining that the outcome of the election, that I over n that I over n people favor candidate 1 is you need one, I candidates drawn from here and n minus I candidates drawn from here. And so the fraction that you thought would have voted for candidate 1 is I divided by n, and that just corresponds to the number of ways in which that choice is possible. And that's what this represents. And that's what this plots. Okay. So sample variance goes down with the size of your sample. But once you have a fixed sample size, the sample variance doesn't really matter as to the number of the size of the population. So you don't need more than some, for one, and so all that determines the accuracy you need, all that determines sample size is the accuracy you need. So if you wanted to get to, let's say 0.1% accuracy, then you need a sample size bigger. Yes.
Let's say if population size is varying, if population size is varying then can we have a same kind of, or we will have to change sample size? Let's
I mean,
say
I think the point is that it's showing here that the sample population size doesn't matter, right? This is the point.
yes, that's. I mean, you are. That's why I'm asking. So, I mean, let's say our population is increasing, which is not possible. But let's say it is increasing at the rate of 10% per year. If we take a sample
But
right now, and then
why do you think
after
that's a
10,
relevant question? Why do you think that's relevant? Well, no, I'm not. I'm asking you. Maybe the more precise question is, what about that scenario do you think is relevant for an election poll? Is my question to you.
I mean,
So how do
yes,
you think that could affect the answer? I'm curious to hear your logic.
I mean, your whatever you are saying, sir. यहाँ पर जो है ना, ये जो 10,000, 1 lakh and 1 cent. That means we should not worry about population size. That means if अगर population naturally vary करती गई तब भी ये शायद नहीं कर.
No,
I
I
mean,
understand what you're asking,
even yes,
but I'm curious. For an election poll, why do you think the population is increasing? I'm trying to understand what you are like,
no,
where you
no,
think that's going to
not
affect.
not in case. No, no, sir. In not in case of population size. And I mean in election.
Yeah,
इलेक्शन में तो नहीं होगा ना ऐसा, वो तो फिक्स होगी.
yeah, yeah.
ये
No,
वैसे
no. So okay.
हम्म,
Uh, I understand what you're asking. I'm trying to encourage you to articulate. I'm trying to get you to say it into words. What is your worry? Because this will yourself allow you to see what the answer is. So please tell me. So explain why. So you're saying that the population grows 10% a year, right?
yes sir.
Yes. So how could that have an effect on a election poll? How do you think that could have an effect? In what ways could that affect an election poll?
इलेक्शन इलेक्शन के केस में तो सर, आई मीन मोर और लेस इन इलेक्शंस केस population is constant.
Good. That's the point, right? Is that there are things that you should worry about, and there are many things you should worry about, and you should always be aware that there are assumptions that could change. But there are often times when you can neglect certain approximations, right? And in this case, because the election poll is happening, let's say over the course of a few days, you can approximate the population as being approximately a constant over that time. Doesn't change very much over a day. And so in that case, I would say that the population growth is not going to have too much of an effect, right?
Mm.
But let's say, this actually happened with, let's say, Brexit polling, right? The eligible voter population changes over time, precisely because people get older, right? And so if you do that, even if you
like
yeah.
you can say like the COVID cases are increasing day by day. So if we want to test them, population is number of people who are infected. So let's say if positivity rate is very high, and in that case population is varying very rapidly. So in that case, I mean that will be the best good example for varying
Okay,
population
that's a better
size.
example. So then you tell me what the conclusion would be from this exercise. What do you think is the conclusion?
Conclusion, as per this, there should be no number of samples should be sufficient. That will not change the result if population is varying.
If the sample is random enough, indeed.
Yeah.
Right.
Yes.
So indeed. So in an example like this, so actually the COVID example is a good one, right? So yes. So you don't know, like every day it's blowing up or it's going down. Who knows, right? So you don't know what the true sample size. You don't know. No. Well. I mean, I think the population. I think for COVID you really have a fixed population, right? What's changing is the fraction, right? The fraction over time, and you're trying to estimate it using a finite sample size. The statement here is that provided that the sample is random enough, then in order to get a 1% accuracy on the true prevalence rate, then you don't need a very big sample. And the problem with these zero prevalence studies that we've seen in India is that they're clearly not random samples. I mean, I can assure you they're not. At least in the cases, for instance, where I read the details of what they did in Mumbai, which is, where I'm from, where I'm very familiar, I was just like, there's no way this is true. Because what they did is they went into some localities and they went into like, one slum area, and then one, they were very, very specific about how they sample things. And Mumbai is it's like it's a city that's like on 2 train tracks, and there's huge population centers around every train track, right? And there's lots of stuff in between. And so the sample wasn't very random. But if you are asking for how, so if you ask, so this is exactly the point of this exercise, is that if your sample is truly random, if you wanted to estimate the current prevalence at any given time of the number of people infected with COVID to within 1%, you probably don't need more than a sample size of 10,000. Maybe even less, actually. I have to work out the details. But that's the point, right? It's the quality of the sample and not the size of the sample that determines your accuracy. Does that make sense?
Yes, sir. Now it is clear.
Yeah. So this is not intuitive. Okay, this is very surprising. Like when I learned this, I was surprised also. Okay, like it just seems like to me crazy, right? That like how can you understand, the voting intentions of 1 billion people, or like in America, let's say 300 million people, from just asking 10,000 people. If you ask 1,000 people, you're actually going to get within 4 or 5% accuracy, right? Or 3% actually. So that's really interesting, right? I mean, and so it's very counterintuitive, but it's nevertheless true. So I really advise you to think through this example, right? Is this, what we're doing here is we're really just considering a situation where you have some fixed amount. We have a sample size. Some fraction is 1, some fraction is 0, and you're just randomly blindfolding yourself and just pulling out, some n number of samples. You don't know where from, and you're asking, what is the fraction in the sample I have in my hand, as opposed to the full sample, right? And so by doing this exercise, you'll realize that the probability of obtaining a fraction I over n is given by the number of ways you could have pulled I from here and minus I from here. The probability of pulling I from here times the number of, so the probability of pulling I from here and minus I from here is the number of ways in which you could have pulled I from here, and times the number of ways you could have pulled n minus I from here, divided by the total number of ways you could have pulled n from m, right? And that's what this fraction is. And the Jupyter notebook that we have up in the collaboratory, where is it? I will. Here we go. So you can play around with this, right? So this is for. So you can everybody see my screen still?
Yes, sir.
Yeah. So here, so really all of this is the I'm asking Python to evaluate this quantity for different values of I being how many samples, so whether we get 0 or 1 or 2 divided by n, assuming that exactly half of the people are going to vote for a particular candidate, and you can just mess around. Let's say we make n is 1 million, and we have a sample size of 1,000. What does the sample variance look like? It could take a while sometimes, but let's see what it does. To evaluate, I guess 1 million was too much for it. Oops, I actually probably had to. Here, I have to do this first. There we go. So you can sort of play around with this and see, for instance, how sample sizes work. So this was for 1 million. That could make it even to 100,000, and you'll see that not much will change. So just play around, and you can make the fraction not a half. You can make it maybe a quarter. So here what you'll find is that the probability will now peak. So only a quarter of the candidates, a quarter of the people are going to vote for one particular candidate, and so you should see that peak shift, and then so do play around with it, but I think the main point is that here, where am I looking for this? Yep, is that it's really something I hope you can intuitively see come true. Okay, so we should. I just wanted to end with a sort of entertaining but very brief discussion of some elementary political science, and maybe help us understand what's happening in our country with our democracy. And it's a really stupid. Okay, so one of the things that you'll see in science is that we often take very, very complicated situations and we make them so simple that you think this is completely stupid. How can this have anything to do with reality, right? But the power of abstraction is we try to draw conclusions in a fictional mathematical universe because it's simple, because we can. But sometimes because it's so simple, we see things happening that maybe, they help us understand really what could be going on in the more complicated system. So part of, if you like, the art of doing data science or science in general is knowing what to ignore. And so I'm going to present to you a really, really simple theory of voting. And then we'll move to the problem set. The theory of voting is called the median voter theorem. And this actually allows us to understand very cleanly something that we have been noticing that's happening in many, many countries, not just India, but also in the US and in the UK, anywhere where there is what we call the first past the post electoral system, meaning that the candidate that just gets any majority, however little, wins. That's it. Okay. Just so you're aware, this is not the only electoral system that exists. So in fact, if you follow any election in Denmark or Germany or the Netherlands or Sweden, in all these Northern European countries, Austria, Switzerland, it seems to be a Germanic thing. It's really complicated. Honestly, I don't understand. Like, nobody can explain to me what's happening because they have a very complicated formula, right? When the elections come in, you need a certain minimum number of votes for your party even to enter parliament. And then what happens is they arrange things in such a way that it is proportional representation. If 30% of the people voted for this party, then that party only gets 30% of the seats. Okay? So if we had a proportional representative system in India, the BJP would have less than, it will have like a little over 100 seats in the Lok Sabha. Okay? Because they only got 30% of the popular vote. Right, so they would still be the largest party, but they would have to govern.
So that was in best case scenario. Otherwise, they will have only 18%. I mean, as per previous record.
Yeah, okay. So you see, so you see the reason we have to suffer under a BJP government is because we have a first past the post electoral system. And if we had a representative electoral system, we would have something that is much more reflective of the diverse makeup of our country, the linguistic diversity, population diversity, like the religious diversity, the socioeconomic strata diversity, and so maybe this is something for all of us to think about as to maybe agitating for a second republic. I think India does need some very, very important constitutional reforms, we should dream about such things because this is, first of all, it's more democratic, it's more fair, and second of all, what I'm about to show you should scare you, because what I'm about to show you in a very simple model shows you why things are happening the way they're happening. So it's called the median voter theorem, and it's very, very simple. The idea is there are only two candidates, okay, in a first past the post electoral system. That means whoever gets the most votes wins. And let's now assume we have this very, very stupid cartoon simplified model where the election is campaigned only on one issue. Okay, this can be generalized to multiple issues, but let's just stick to one for this argument. And let's say that issue in this case is whether taxes should be high or low. Okay, so very often, people on the the left or the socialist side want higher taxes so they can pay for more social services. And then in India we have the Brahmin Baniya complex, but in the West we have like essentially just the capital, like the people that control the capital, right? And so they want low taxes because they don't want to pay for everything else. They just want to be rich and have all the wealth and treat everybody else like a slave. Okay, so this is and under the U.S. they've done this amazing thing where they managed to convince. You see, every country has worms in their brains. Okay, like Indians, we have many. Americans, they have many. British people, they have many. And in America, what they've done is they've managed to convince people that there's this thing called freedom, which they don't have, but they managed to convince them that essentially to vote against their best interests. So the ruling classes of America have figured out, then this happens in very, very sneaky ways, primarily to the media, but it's very subtle, that somehow their freedom is important, that they're independent Americans and no one should be able to tell them what to do. And so the taxes should be low and the government shouldn't get into their way. And so there is a country, the most powerful country in the world, has bridges that are collapsing right now. One of the main bridges that connects across the Mississippi River, which is a huge river, by the way, has been shut down. And so in one of America's biggest cities, Memphis, people are not able to get from one side of the river to the other. They have to take they have to drive like 2 hours in a different direction. So very often people's voting intentions can be really, really distorted by the elites. Okay, in India we have our own version. So but in this simple example, getting back to simple example, is the median voter theory. Okay, so basically we have two candidates, first past the post, whoever gets the most votes wins. And let's say there's only one issue, whether taxes should be high or it should be low. Now, in general, the population will have some distribution of opinions. Some will feel very strongly, some will feel in one direction, some will feel very strongly in the other direction. More or less, typically, the people are neutral, and there's a general sort of opinion that's sort of around some center. Okay, whatever that center is. Okay, let's say now it's most people be like, let's not have it too high, let's not have it too low, something in the middle. Okay, so this is what happens. And now, let's say we have two candidates, A and B. Candidate A is an extreme right-wing capitalist person and believes in very, very low taxes. But candidate B is sort of left of center, believes in moderate taxation. They shouldn't be so high because we do want whatever. So these are the two opinions. So the median voter theorem says, and that's the median voter theorem. The median voter theorem is that we pick the candidate whose opinion is closest to ours, which seems reasonable, right? I mean, if I'm somewhere over here, if I favor slightly low taxes, but not, but maybe less in the population, this guy favors way, way less taxes, so that's too much for me. But this person favors a bit high. I can live with that, so I'll vote for this guy. Okay, this is the median voter theorem. So because what the median voter theorem implies is that in a situation where the underlying population distribution is let's say centered around some center, candidate B wins. The candidate closest to the median of the distribution, the median, by the way, is the 50th percentile. That means imagine 0% of the voters are here, but then 1%, 2%, 3%. And by the time you get to the 50th percent, you're somewhere over here. So in this case, the mean and the median is the same. So the candidate that is the 50th percentile of the population, and this is the 100th percentile is here, then candidate B wins. So this is a typical situation that we would have had, let's say, 20, 30 years ago in many countries. But what if you polarize the population? Okay, so now what we have is the population itself is divided, and we have two extremely opposing camps, right? One really is a large number of people that favor low taxes. There's a large number of people that favor high taxes, and let's say, for the sake of argument, they're roughly the same number of people. Now, what the median voter theorem implies is that the centrist candidate loses, okay? Because candidate A is closest to the median, right? And so in this simple example, and by the way, this can be generalized to multidimensional axes of choice. Okay, this conclusion is inevitable. Is that once the population is polarized, you have basically favored the extreme candidates. And this is how our democracies have been hijacked all around the world. Because how do you go from here to here? Is through media manipulation, through capture of institutions, through in India it happens in a particular way. In America it happens in don't be under the impression that other countries are better than India. I mean, they have, in a lot of ways, I think America is a really messed up country. I've lived
Sir,
there long enough to, yes,
sir, sir.
yeah,
I mean, there are politicians who make very stupid statement, but
yeah,
I don't think they. I mean, it seems that they would not have made statement. So, is this the reason that they are making statement just to polarize only
absolutely.
without? So that's why mean should be
Absolutely. This is Amit Shah's strategy, right?
okay. Okay,
Right?
okay.
They say things to piss people off. They want to drive people more to one end and drive other people away because they know that their candidate's going to be more extreme. This is how we're being manipulated. Okay. And this is happening, exactly. They polarize people. They feed them false narratives, right? I mean, this whole tablighi Jamaat thing at the beginning, right? It was completely made up, right? They said that, there's this tablighi Jamaat, the super spreader event at the beginning of the pandemic, and this is what's causing it. Meanwhile, all across India, hundreds and thousands of people are meeting in temples and different places, and they don't talk about them, right? And so what this does is it makes the population really upset, and then you start seeing things in news. If you're unfortunate enough to have to watch English news in India, it's a disaster. I think the vernacular, well, actually in Hindi is pretty bad, actually. But if I speak Marathi, so I watch a lot of Marathi news. It's a little bit more sensible, but it's not great either. But if you feed people poison, they're going to get polarized in their population. And then we have like WhatsApp University garbage and stuff. This is fueled by the IT cell of the BJP. They want this to happen.
Sir, it was
When this
happening
happens,
in villages. Our
yes,
villages, people were not talking to Muslim guys. It was
yeah,
so bad that I was feeling so bad for them, sir. It was
yes,
really,
yes,
really bad.
yeah. But this is what happens. You see, we used to be this. Now we're this. Okay. And by the way, this is true everywhere. Yeah, this is not just true in India. This is true. This is how. In case it's not apparent to you guys, I do have some fairly left-leaning political views, not political, economic views as well. And I think primarily the axis of oppression in India has other caste dimensions as well, but there's also a class dimension as well. Is that this is how the elites figure out how to keep power. Okay, there is so much money and power and decisions that are being made behind doors that we cannot see. There's a game of chess being played over our heads, and these people know exactly what they're doing. And what they do is they back candidates. So why is it, for instance, that Modi and Shah are so favoring industrialists, right? I mean, they are very business friendly, right? That has nothing to do with their Hindutva politics in general. In fact, Hindutva should be against this, right? They're doing what the reason it's happening is because the people who have money are backing you because they know that if we just give them money, they will do as we say, so we make them in power. The minute it flips, the minute the money leaves, the RSS and the BJP, it's game over for them, right? And so because what will happen is that this will maybe go in a different direction. Maybe it'll go back to this. I don't know, but it's the elites to the control of their media. It's the control of institutions, educational institutions that causes this over time. It takes time. It doesn't happen right away. And the BJP has been at this for 20, 30 years, been at this since independence. But it finally happened, right? And this is where we are. So this is why we have extreme candidates winning. So look at let's take a simple example of the Delhi elections, right? Where who was it? I think there was an Aam Aadmi Party candidate, and there was I forget who. It was the Delhi the Lok Sabha elections. I think it's maybe even I forget. It was someone really like this the AAP the Aam Aadmi candidate was was an activist was has written books, was really the perfect candidate, but she was too close to the center, and then the more extreme candidate being like, like what are these, Muslims this, Muslims that, and then so therefore, even if this is a small bump and this is a bigger bump, even if this was like small and this was huge, the point is this candidate is still closer to the median. So this is how the median voter theorem is showing us that the elections are. This is how democracy can get hijacked. So essentially, first past the post electoral systems can be manipulated, and that's bad. So that's all I wanted to say. We're going to now turn to the problem set. Um, I actually I have to run in about 20 minutes. So, but there's only really two questions that we had to go through. But the main, you see, so in the course of these sort of introductory lectures, we covered fraud detection, we covered COVID-19, we covered election polling. We picked them because we wanted to hit all of the main central concepts that underlie statistical inference and statistics that you will need to be able to be a data scientist or to be able to do your own data science. And by the way, these courses that we're designing, you don't have to take them just because you want to be a data scientist. You should take them because you will then have power to do your own analysis for different things, right? And so this is really a valuable life skill that I myself use for my own decisions. And this is what we wanted to cover. We covered lots of things. We covered lots of very, very advanced concepts. And so let's hang on, let me close this. Let me get to the problem set. Here we go. So you can see my screen, right? Still?
Yes, sir.
Okay.
Yes, sir.
So look, this is really more of a write-up, in inviting you to so I'll post solutions, but it's really a write-up for you to see concepts such as estimator bias. Okay, and this is really, really a central concept, and this is central to machine learning, by the way. So we really you should, and it's central to all of the data science that you'll be doing, which is that we have a finite sample size. We're trying to estimate some quantity. So in the case of an election poll, we're trying to estimate, the fraction of people voting, let's say the mean of some value. But then we know that the true value is something, and the bias is even if you did it perfectly, whether your estimator actually converges to the true value or not. And so what this exercise was trying to show was that the naive thing for finite sample size of estimating the mean and estimating the variance this quantity is actually what we call a biased estimator. It doesn't actually converge to the true value. So this should be intuitive, right? If you're trying to estimate the mean from a finite sample, just sum up all the values and divide by n. That's the mean. That's fine, right? That's of course. But when we want to estimate the deviation of a given from the mean of whatever samples we have, we only have our estimate to deal with. So we have to put in mu bar here instead of the actual value mu. Okay, mu is the true value, right? Let's say we had the true. Let's say n went to the full size of the sample. We don't have access to that, so we put in this quantity instead. And if you think that we obtain that by dividing by n, it turns out that that's actually biased. And to get the truly biased value, you have to divide by n minus 1 instead. And that's what this example was hoping to walk you through. And so this proof that the variance of n of a sample, if we have a particular variable with a variance of sigma squared, then if we repeated that n times, then the sample variance being sigma squared divided by n, this is what this part of the exercise was trying to prove. And it just follows by induction, proof by induction. Okay, so I hope this is something you should be able to follow. But if not, please just we can still you can ask me questions on the stream or by email, and I'm happy to answer. But Modish had a question about how we go what the steps are in equation 5. All I'm trying to do is I'm trying to estimate the bias of this estimator for the variance. So I take its expectation value and I compare it to the true variance, which should be sigma squared, right? So if I just take the average of what I construct as this estimator, I'm just taking the actual average, and what I do is inside here I just subtract and add the true mean. Okay, so this is the same equation as here, and because and when I do that, I can just rearrange terms in this way. Okay, so from here to here, these two quantities inside the angle brackets are the same. Just write it out, and you see that they're the same. Okay, and so when you do that and you follow through, and then you realize that the variance of the sum of a variable is the sum of the variances. That's what this proof was trying to show. You can show that the variance of the average is in fact, it's just sigma squared divided by n. And you will see that your estimator, in fact, is biased, and it's biased by this amount. So you have to divide by 1 over this amount to get the true estimator, and that's why we use this for the sample variance and not this. Okay. So if you have trouble following that, I mean, I hope you don't. I think I think what I found actually is that you guys are much smarter than the level of the course that we've been preparing for, which is someone who's never seen anything like this before. And this example, these questions should be straightforward. I'll post solutions so you can see where this comes from, or maybe I'll post some extra, so I'll post some extra explanations in the solutions. But the main point is that this exercise shows that if you had an estimator that was the original estimator plus some function, which is a random variable with 0 mean, then you will also arrive, and this will be also an unbiased estimator. Okay? Now, this seems abstract, but what this corresponds to in reality is, imagine you have noise. Okay? Very rarely in a situation do you get clean answers, right? So in case of flipping a coin, there's not very much noise. But let's say we're trying to measure some number out there. Let's say we're trying to measure some, I don't know, some voltage in something. There's always going to be some little fluctuations, but provided that those fluctuations average to 0, it doesn't matter if you introduce noise. The estimator is still unbiased. Okay. The problem is when you start to construct a variance with noise, then you'll find that in fact it is a biased estimator. The noise, you have to subtract the noise correlation function. So, so that's some extra material here, and this is something that I just wanted to show you because it's going to be seen as something that it's actually straightforward to derive, but you need to know a bit of calculus. So all I'm going to do is I'm going to state the result, okay? And by stating the result, I'm simply saying. So very often we have a situation where we don't know what the underlying distribution is, but we're trying to estimate it using some finite sample. Now, if you keep repeating that estimation, you're going to get fluctuations around the true value. And what this bound, this is known as the Kramer-Rao bound, is telling you how big those fluctuations would be as a function of the size of your sample. And it turns out that this quantity here, this IAB, is known as the Fisher information matrix. And it's just, and so if forget that I have these, so in general, a probability distribution function is going to depend on multiple parameters, the mean, the variance, so on and so forth. But let's say we have just a distribution that just depends on one number, let's say a Poisson process or something, it's just one number, right? So there's no A, B, so then just ignore the A and the B here, it's just one number. What this number is the change in the likelihood as a function of how you change that parameter. Okay, so I'm going to switch to my Blackboard, my thing here, just to illustrate this with some with a cartoon. Okay, so let me. So can you see my my writing, or is it backwards?
Sir, it is reverse image.
It's reverse image. Okay, so let's see. How about now? Is this okay?
Yeah, it's okay.
So, okay, so recall that if you have some probability distribution function for some random variable that depends on some parameter. Okay, in general, it could depend on many. So let's say the Gaussian, right? Okay, but it could be more general, right? So, for instance, let's say, for instance, so the example we had in a previous homework example was flipping coins, right? So, what the likelihood function is, the likelihood is viewing the probability, viewing the data is fixed, and then viewing the fixed data as a function of some underlying parameter. So imagine we have a situation where, let's stick to the election polling example, where you ask, let's say, 8 people whether they're going to vote for candidate A or candidate B. But you know, in reality, that the probability for someone voting for candidate A is given by theta. Let's just say it's some number theta. And so therefore the probability that they vote for candidate B is 1 minus theta because there's only 2 choices. Right? And so therefore, if you ask 8 people and they give you answers A, B, A, B, 1, 2, 3, 4, 5, 6, 7, A. Okay, so you from your random sample, you just happen to come across this set of events, and you ask yourself, well, what is the probability of obtaining that? Well, I know that the probability of A is theta, so this is theta to the 6th, 1 minus theta squared, right? It's the probability of obtaining 2 times B, and the probability of obtaining 6 times A, and they're all independent. Okay, so if I were to plot this, right, I'd find that that this function here is a function of theta, the likelihood is a function. So this is the probability of the data, which is here, 6 times A, 2 times B, as a function of theta. This is equal to this. I'm just defining this as the likelihood. So this is going back a couple of lectures, but this is what the likelihood function is. If I plot this, I find that my likelihood function looks like this, and it's settled around the fact that the probability, this peaks around a probability of theta equals 0.75 or something like this, approximately. Okay? But in reality, let's say theta is, I mean, we don't know. It could be, let's say, it could even be a half, right? But the thing to notice here is that this is my likelihood function, and my likelihood function could look like this. My likelihood function could look like this. Okay, it really depends on the underlying system, right? My likelihood function could look like this. Okay, what this is telling us is if we're trying to infer what the true value of theta is from our finite sample, a reasonable thing would be to just estimate that it's the maximum likelihood. This is called maximum likelihood estimation. Okay, obviously, if we repeat the experiment enough, many times, that this becomes more and more peaked around the center. But for finite sample size, we're always stuck with this kind of spread. And so, how are these 3 situations different? Okay, let's say they all had a maximum likelihood estimate of theta equals 0.75. These 3 situations differ in the following sense. You can be much more certain that the true value is 0.75 because a small deviation away from 0.75 makes the likelihood go down a lot. And here you're less sure because although the likeliest outcome is 0.75, a little change, actually it's still just as likely. So you're less and less sure. Okay. So what the Kramer-Rao bound, so if we call this quantity here, so if we're looking for the change in the likelihood function divided by the change in a small delta theta, right? If this quantity could either be, in this case, this quantity is very, very small, right? So this quantity in this case is let's say it's very, very small. It's much, much less than 1, right? But in this case, the change in the likelihood divided by change in theta is much, much bigger than 1. It's huge, right? It drops all of a sudden, right? If you just go a little bit away. Okay, so what the Kramer-Rao bound is, and so if I take this quantity and I square it, right? So if I look at the square of this quantity, here, what the Kramer-Rao bound is saying is that the variance of your estimator for finite sample size, if theta bar is my estimator for some value, if I take its variance, is going to be greater than the information divided by n, where n is a sample size, where this information is 1 over n times the average of the change in the likelihoods divided by d theta. So this is very, very advanced stuff, guys. But I wanted to show you it because it's intuitive. It helps you understand intuitively what's going on. So what that's saying is that when the likelihood function is very sharply peaked, okay, when the likelihood function is like this number is huge, this number is, so this is a very, so the thing that's multiplied, so this is equal to 1 over n times some number, right? If the likelihood is very sharply peaked, this number is very, very small, right? And so your variance, the fluctuations in your estimator as you take more and more samples is small. That means you can be more and more sure that what you're seeing is close to the true value. Okay, but if this number, if instead the likelihood function was like this, okay, right, then this quantity is closer to 0, then this number becomes big, right? So instead of a small number here, you have a very big number, right? So this much less than 1. Sorry, this much less than 1. And now this number is much bigger than 1. Which is saying that this number is huge. That means your variance, your fluctuations are going to be huge. You're getting lots and lots of fluctuations. So a random trial, you're more likely to be very far away from the true value. And that's the content of the Kramer-Rao bound. So it's something that tells you deep. So if you just have a random data set, it is actually an alarm. It's like a little red light on your data set that's telling you when and where to trust, how much to trust your estimator. And it is a central concept in statistical inference. We'll be seeing it implicitly again and again. We won't, and what I'd like to do is I'd actually like to derive it with, if we can ever assume calculus, I'd like to derive it for you. Because it will come up in machine learning, it will come up in data science, but anyway, that was it for today's Q&A session and mini lecture. That's it also for our invitation lectures. As I mentioned before, we are immediately going to try and set up a coding academy. It might take us a week or two to get the right people together to do it. But what it will be is an introduction to Python. I understand that some of you are already getting together and learning Python by yourselves, which is fantastic. I'm very happy to hear that. But also RStats. There's a special package called RStats, which I actually don't know very much about either, but because I primarily use my own specific software. But we'll have some experts come and introduce you to RStats as well, because the combination of RStats plus Python is central to, is industry standard. It's used by data scientists like all the time. And so we'll have a little coding academy, maybe take a month or two, probably about 2 months. And as soon as we all know how to code, we'll come back and we'll do a second module. And we'll have another intake and maybe more people will join us. So that's it for today. Do you guys have any, I have about 3 minutes. Maybe we can have a few short questions if you have any, or comments or anything. Okay, so I'll post the links to the Jupyter Notebook for looking at the sample variance for finite sample size for an election. I'll post additional links to go along, and I'll post solution sets for the problem set today. I want to remind you again that I'm available over email, and even if it's about anything, you don't have to just ask me about data science. You can, if you have any questions about anything else in life or anything, I'm very happy to talk. But what we'll do now is the formal induction, if you like, the invitation lectures are concluded. More material will be added over time because we want it to be a permanent thing on the digital Nalanda website, and so it'll be improved. If you know any people that may be interested in the future, let them know that there'll be another batch, maybe 6-7 months down the line for the induction lectures. But But anyway, so you can look forward to hearing more. There will be another call from Digital Nalanda for the Coding Academy. It will be open to people not just interested in data science, because it's a useful skill to know anyway. But yeah, so we'll pick up again in a couple of weeks, and I hope to see you guys. Okay. So that's it for the meeting. Thank you, everyone. Jai Bhim to all, and hope to see you soon. And let's keep in touch. Okay. And the course, Google, the classroom website will stay open. The stream will stay open. We can still chat and post material and discuss that. Okay.
Thank
So
you,
good
sir.
evening,
Jai
everyone.
Bhim.
Jai Bhim. I have to go now. Okay. Bye, everyone.